Hey guys, welcome to Mestris YouTube channel. Today we'll be discussing a question on hydrostatic pressure and buoyancy, which was asked in GATE 2005. So let's read the question first. Cross section of an object having same section normal to the paper submerged into a fluid consists of square of sides 2 meter and triangle as shown in the figure. The object is hinged at point P, that is 1 meter below the fluid free surface. If the object is to kept in the position as shown in the figure, the value of x should be. So what we have here is an object like this. It is a composite shape consisting of a square 2 meter by 2 meter and a triangular part. So here we have a hinge at point P, and the question is to find the value of x if the object is to be kept in the position as shown in the figure. For the object to be remained in this position, the body should be in the equilibrium. And if we talk about the equilibrium of the body, we want the body to be in horizontal, vertical, and moment equilibrium. We want these three equilibriums to satisfy to say that a body is in equilibrium. Since we are having a hinge here at point P, this hinge would be restraining any horizontal and vertical movements of this body. That means just keeping this hinge here, both horizontal and vertical equilibriums are satisfied. Now we just want to consider the moment equilibrium of the body. That means the net moment taken about point P should be 0. And for that we will first consider the horizontal force acting on this surface and the surface. We know the pressure force will be varying linearly with respect to depth, and the total pressure force at the surface will be the area of this distribution. So here it would be gamma of W into this height, that is 1, and this is a distribution, and the total force would be the area, that is and it would be acting at the centroid of the distribution, and here it would be 2/3 of the height from the top vertex of the triangle. So it would be uh, this distance would be 2 by 3 of the height. Height is 2, so it would be 4 by 3, and 4 by 3 is 1.333. It would be like here. This would be the total force acting. And if you consider about the other side, the pressure distribution would be the same, and the centroid would be the same also. That means it will be from the top vertex. It would be 2/3 from 2/3 of the height. That is 2. That would be 4 by 3. And we can see that these two forces, that is these two total forces. This is the total force acting. This is the total force acting at this side, that the right side, and this is the total force acting at the left side. And these two forces would be collinear. That means the moment due to these two forces about the point P would be 0, would be cancelled out. That's the exact point. So the net moment made by these two forces about point P would be 0. So for horizontal forces, we don't have any moments, and if we consider the vertical forces, the since nothing is told about the weight of the body, we will be neglecting the weight of the body, and the only other vertical force that is acting on this body would be buoyant force. Buoyant force. And buoyant force is nothing but the weight of the weight of the liquid displaced, which is equal to volume of the body into specific gravity of the liquid. That is, here it is water, so gamma W. So if we consider this body, if this is a composite shape, so we will consider this as a square and a triangle. And for this square part, there will be a vertical buoyant force. Let's call it as VB1. And for the triangle part also, it will be a VB2. So VB2, VB1 would be the volume of the square part, the area of the square volume can be written as area into thickness. Area would be 2 into 2, and the thickness, let's take it as a unit thickness into the plane, so it would be 1, and into gamma w. Gamma w is, let's take it as gamma w only. And for VB2, we have the area of the triangle, that is half BH, half into B. B is, let's take it X, and the height is 2 meters, so 2 into gamma W. So we have 4 gamma W and X into gamma W, X into gamma W. So if we consider the position of this VB1 and VB2, the buoyant force would be acting at the centroid of the body. So that would be, here it would be at distance 1 meter, that is, this distance is 2. So the buoyant force would be acting at the center, so it would be 1. And for this triangle, it would be acting at the centroid, so that means this would be 1 by 3 of the x. So this would be x by 3. So if we try to take the moment about P, let's write moment about P. Let's scroll down a bit. So if we take the moment about P, it would be VB1 into 1. It would be, if we take the anti-clockwise as positive, it would be clockwise direction, so it would be negative, and VB2 into x by 3. Since it is anti-clockwise, it will be positive, so plus VB2 into x by 3, which should be equal to 0. Since the body is in moment equilibrium, this should be equal to 0. Let's substitute, and VB1 is minus 4 gamma W plus VB2 is x into gamma W into x by 3. So gamma W can be taken to the other side, so it will be gone. And here we have x square, so we can get x square is equal to 12. And here we can know x equal to root of 12. So it will be root of 4 into 3, that is 2 root 3. So we have our answer as 2 root 3, and here we can see 2 root 3 is an option. So this is our answer. That's it, guys. Thanks for watching.